Chapter 8, Sections 4 and 5. The current gain in all discussions that we've had up to this point has been what's known as the DC current gain, which is defined as the beta DC, which is IC over IB. The currents in this formula are at the Q point, because the curvature in the graph of IC versus IB, the DC current depends strongly on where you are on this curve. So when you set up your resistors for your to bias your transistor, that's what determines your Q point. So this beta is solely depending on where the Q point is, because this Q point varies depending on what IB and IC are. In order to discuss amplifiers, we define what's called the AC beta, the AC current gain. This equals the AC collector current divided by the AC base current. So graphically, beta AC equals the slope of this curve at the Q point. So in review, the beta DC is given by IC over IB, and these are DC currents. The AC current is given by the beta AC, which is IC over IB so this is the slope at the Q point. So the Q point location really is solely dependent here, because the size of the emitter current depends on the location of the Q point, as you can tell from the graph. So if your Q point is here, you have a different kind of output than if your Q point's up taller, up higher. You get a much higher, much larger emitter current. So we define the AC resistance of the emitter diode as inversely proportional to the AC emitter current. In other words, as VB goes up, RE goes up. So the AC resistance is defined as RE with a little prime on it. So the prime tells us the resistance is inside the transistor. And we're going to use this later on when we model transistors. We're going to analyze them by modeling them. So this resistance will play a key factor. An alternative formula for the AC resistance of the emitter is given by the following formula: 25 millivolts divided by IE. Our book doesn't derive this formula. More advanced books in electronics go through and derive this formula. So let's look at an example. Let's calculate RE prime in the following amplifier. So here, this is a base bias circuit. The DC base voltage is 0.7 volts. And because 30 volts VCC is much greater than 0.7 volts, the base current is approximately 30 volts divided by 1 million ohms, which is 30 microamps. I mean, if you didn't want to ignore the 0.7, you'd have 30 volts minus 0.7 divided by 1 million. So, it's a lot quicker just kind of round it off and assume the VBE here is approximately 0 compared to 30 volts. So with a current DC gain of 100 in our circuit, that means the collector current is 3 milliamps. 100 times the 30 microamps. So therefore, the AC resistance of the emitter diode is 25 millivolts divided by 3 milliamps, or 8.33 ohms.